Hello, and welcome to this screencast where I'll be doing some examples of definite integrals using substitution. This is an area where students sometimes get a little tripped up, and so I want to highlight some of the things that you really need to keep in mind as you're solving problems this way. So let's start out here, and as in the previous video, this is one that you might be tempted to say, well, why don't I just multiply this thing out? I don't really want to multiply that out. There's lots of room for error there, so let's see if we can be more clever about this. And so let's try looking at this, and we see something in the parentheses here that we don't quite see the derivative out there, but we do see something with an x squared. So let's see what happens here. Let's let v equal x cubed minus 3x plus 2. And so then dv is 3x squared minus 3 dx. And let's see, I've got an x squared minus 1. Oh, wait a minute. dv is 3 times x squared minus 1 dx with a little bit of factoring. And then I'll get 1/3 dv equals x squared minus 1 dx, and now I have my x squared minus 1 dx, and I can put my v in there. And so if we were doing an indefinite integral and we weren't thinking about our limits of integration, because we didn't have them, we would come in here and we'd say, okay, well this is now v cubed times 1/3 dv. Now here's where we have to be very careful. These limits of integration, we're saying x goes from 0 to 2. This is now a function of v, and so we really need to figure out that what happens with v when x is 0. So we would say v equals, we'll put in x equals 0, so 0 cubed minus 3 times 0 plus 2 equals 2 when x equals 0. And so that becomes my lower limit of integration here. And then we say v equals, well, we get 2 cubed minus 3 times 2 plus 2, which is 8 minus 6 plus 2, which is 4. When x equals 2. So my upper limit is now 4. And now I can just go ahead and do this like the ordinary definite integral problems we've been working on, right? So my undoing the power rule says I need this 4 there, and so I get 1/12 of 4 to the 4th minus 2 to the 4th, and I'm not even going to calculate that out more precisely. That's a number. If we need a precise numeric value, we can go work with it further on a calculator. This is my preferred way to do a problem like this. Now here's an alternative if you don't like, and every once in a while you find a situation where doing these calculations here, where you figure out your new limits of integration, where you find out that that's a little bit tricky. So what is also acceptable is to say, okay, I'm going to leave this from x equals 0 to x equals 2. Reminding myself that this 0 and this 2 are limits for the variable x. And then I'm going to go find myself my antiderivative. And I'm going to say this needs to go from x equals 0 to x equals 2. And then I'm going to say, well, wait a minute, this is a function of v. I need to make it into a function of x, just like I did with my definite integrals, or with my indefinite integrals. So I need to come back here and get this back to be in terms of x. And I'm going from x equals 0 to x equals 2. And now here, it's just the exact same calculations we did before, and so we put in x equals 2, And we get 2 cubed minus 3 times 2 plus 2 minus 0 cubed minus 3 times 0 plus 2. All lost my fourth power. Those things raised to the fourth power. And it's going to simplify out just like it did before. 1/12 of 4 to the fourth minus 2 to the fourth. Okay, but it's very, very critical. One of the key things students forget to do is changing these limits of integration. So I need you to either always change the limits of integration to be for your new variable, or carefully label the limits of integration to remind yourself that you've got to go from your substitution variable back to your original variable. I'm going to stick with the changing the limits of integration approach in most of my examples. So let's look at this one. And here we're thinking, well, I've got an outside function that's the cubing function here with a cosine of pi v inside. So let's try let t equal cosine of pi v, and then dt is going to be minus sine of pi v times pi dv. Oh, great, I have a sine of pi v dv. So let me just move that minus sign and the pi over by division. So now I see a sine of pi v dv is equal to this guy, and then I can put in a t for my cosine. Before I do that, let me go figure out my new limits of integration. So v equals 0 gives me that t equals cosine of pi times 0, which is going to be cosine of pi, which is cosine of 0, which is 1. And then v equals a half gives me that t is cosine of pi over 2, which is 0. So this now is an integral from t, and I'm going to label these just so that we remember. Now v equals 0 meant t equals 1, and v equals a half, it means t equals 0. So even though your inclination might be to say, oh, well, I need to go from the smaller number to the larger number, no, you need to keep them in the same order that they matched up. So this limit needs to be the one that corresponds with the 0 limit, the lower limit over there. Okay, so now we've got t cubed, and then we get times minus 1 over pi dt, because sine of pi v dv is minus 1 over pi dt. And now this is not so bad, right? We get minus 1 over pi, and then we get times 1/4 times 1/4 t to the 4th from 1 to 0. And so I'll keep the minus 1 over 4 pi out here, and then I get 0 minus 1, 0 to the 4th minus 1 to the 4th. And so I get 1 over 4 pi, because that's minus 1, and so that minus cancels. So that's pretty slick, and again, I changed limits of integration, and I'm going to just keep doing that because it saves us the work of actually coming back here and putting this cosine of pi v in for t, which just kind of made things messier and more steps there. I'd rather have separate steps sitting around. Okay, let's take a look at this one. Well, let's see, I've got 3 sine u, and cosine u is almost the derivative of that. So let's let x equal 3 sine of u, so then dx is 3 cosine of u du. I've got a cosine u du, but I don't have the 3, so let's move that over. 1/3 dx is cosine of u du. Now I need to change my limits, so we've got u equals 0 means that x equals 3 sine of 0, which is 3 times 0 is 0, and u equals pi over 2 means that x is 3 sine of pi over 2, which is 3 times 1, which is 3. Alrighty, now we're ready to do this, and so we'll put in our new limits. The 0 limit is still a 0. The pi over 2 limit becomes a 3. The cosine u du part gives us a 1/3 dx. So I'm going to put the dx out there. And then the e to the 3 sine of u becomes e to the x. Now, here's another thing students sometimes do. They get to see this cosine u, and they group it with a du, and they write 1/3 dx e to the x. Well, that doesn't make any sense, because this e to the x needs to be inside the integral. We always need to keep our differential, remember, this is representing this infinitesimally small width of a rectangle. We need to keep that lurking out at the end. And so now this is an antiderivative for e to the x is e to the x. Isn't that slick? And we evaluate that from x equals 0 to x equals 3, and so we get 1/3 e cubed minus 1/3 e to the 0, but e to the 0 is 1, so that's 1/3 e cubed minus 1/3.